Alright, in this exercise we're going to go through and we're going to tune the temperature, and not tune, we're going to use a PID to control the temperature control lab unit. One thing to note here is that proportional control is good for quick responses to error. Integral control is good for non-integrating processes such as our temperature, such as the speed of a car, such as the concentration coming out of a CSTR, processes that aren't integrating, because the integral control will offset persistent offset. It'll counteract that persistent offset. The problem of integral control, though, is that it can lead to oscillations, and so derivative control seeks to minimize those oscillations that usually happen because of large changes, large derivatives in the error. One note here really quick, as we look at our equation right here, is that instead of taking the derivative of error, in practice we take the derivative of our process variable, and we do this so that when we change our error, or we change our set point, the error will have a very large change, and that large jump will cause a very high derivative. But if we take the derivative of our process variable, it will be more continuous, which is better for our control. Let's go ahead now. This is our discretized form. We'll just briefly look at it. Let's look at our PID function. It'll take in the tuning parameters, our set point, the current temperature, the prior temperature, as well as the integral of error and the time between measurements. So we're going to first implement some aggressive IMC tuning. We've done that with our process model, gain of 0.9, process time constant of 175, and dead time of 15 seconds, just like we've had before. Using the tuning constants, we get a Kc of about 8.11, a tau I of 182, and a tau D of 7. And you can use those numbers to check your own numbers. I really like having the semicolons left off for things I want to look at the values. We'll go ahead then. I'll run that section first of all. It's from a previous run. Let's go ahead and let's implement this on the temperature control lab unit. What's going to happen here, and let's discuss this loop now because you'll be constructing these loops more and more on your own. We're going to first measure the temperature and then store that temperature within our time array. Then we'll gather the heater setting at time I, as well as P, I, and D from our PID controller. As we mentioned before, let me scroll over. The PID controller function will take arguments of the parameters, the set point at time I, temperature at time I, as well as temperature at the previous time point, the integral of error, as well as time difference between time I and the previous time step. We'll use that difference in order to calculate the derivative and the integral. Then we implement that heater change with lab.q1, and then we plot it for convenience's sake. So let's go ahead. We'll run the section and connect to the TCLab, and then we'll go ahead and run this and see how well our PID controller performs. I'll go ahead and pause the recording and meet you once we're on the other side. Alright, and here we have our results. You'll notice there's quite a bit of, not chatter per se, because we don't have a valve going on, but there's a lot of up and down action within our heater here on the bottom. And it's mainly due to our derivative action. There's little tiny disturbances due to sensor error, or maybe just the air that's flowing past the temperature control lab, and that causes those fluctuations within the actuator. But you'll notice that over time we have our integral control pushing us until we get right to our set point of 60 degrees Celsius. And so there you have it. We've used a PID controller to control our temperature control lab. Let me know if you have any questions. I'd be more than happy to help.